Good afternoon, my YouTube viewers. It is Crystal, and in this video, what we're going to discuss is A/B testing. So A/B testing, also known as split testing, is a statistical method used to compare two versions of a variable to determine which one performs better. Widely employed in fields like marketing, product design, and website optimization, A/B testing empowers organizations to make data-driven decisions. So there is a process that you have to follow when you are endeavoring to undertake A/B testing. So what we're going to do is we're going to talk about the process. Number one is you have to define your objective. And then number two, you have to create your hypothesis, which is going to be either a null hypothesis or an alternate hypothesis. The null hypothesis is generally there's no significant difference between A and B, and the alternate hypothesis is there is a significant difference between A and B. Then you have to design the experiment. You have to provide a randomized assignment. Then you have to collect your data, analyze results, draw conclusions, and iterate and optimize. So that's the process that you have to follow for A/B testing. So what we're going to do is we're going to go through some examples of A/B testing in R. So the first example of A/B testing that we're going to perform is a two-proportion z-test. Now, a z-test is supposed to be performed in z distributions, which are also known as normal distributions. So this is our two-proportion z-test. Your null hypothesis is conversion rates are equal, and your alternate hypothesis is conversion rates differ. So the first thing you want to do is you want to set your seed. The reason why you set your seed is so every time you run the program, the variables will initialize to the same values. So you type set.seed brackets 1, 2, 3, and you can type any number that you want within the brackets. Then what we're going to do now is we're going to simulate the A/B experiment. So A is your control sample and B is your treatment sample. And so we're going to design a binary outcome being 1 equals the conversion and 0 equals no conversion. So in A, which is going to be your number of samples in A, is 200, and in B, which is going to be the number of samples in B, is 200. So we're going to control converts at 12%. So A becomes R binom. That's a randomly sampled binomial distribution, brackets in A, so that's 200, size equals 1, probability equals 0.12. And then now we're going to do treatment converts to 18%. So B becomes a R binom, which is a randomly sampled binomial distribution of 200 samples, size equals 1, and probability equals 18. So we're going to do our conversion counts. So conv A is the sum of A, and conv B is the sum of B. So now we perform a two-proportion z-test, which is a proportion test utilizes chi-square approximation. So the test result becomes prop.test brackets x equals c, that's a vector of conv A and conv B, and n equals c is a vector in A and in B. And then so correct equals false, which turns off Yates correction for clarity. So now what we do is we print off the test result. So you've got a two-sample test for equality of proportions without continuity correction. So data is a vector of conv A and conv B out of a vector of NA and NB. X squared is 1.2216. Degree of freedom is 1 because we have two samples, and then you calculate the degree of freedom by taking the total number of samples and subtract 1 from it. So 2 minus 1 equals 1. Your p-value is 0.269. So since the p-value is greater than the significance level of 0.05, that means you're going to fail to reject the null hypothesis, which means there's no significant difference between the two samples. So your alternative hypothesis is two-sided, but we're going to fail to reject the null hypothesis since your p-value is greater than the significance level of 0.05. So you have a 95% confidence interval, which is 0.11 to 0.03. And then your sample estimates of proportion 1 is 13.5% and proportion 2 is 17.5%. So we go back to the program. So we plot the conversion rates with confidence intervals. So conversion proportion. So PA becomes conv A divided by NA, and NA is 200. And PB becomes conv B divided by NB, and NB is 200. And now we calculate the 95% confidence interval for each group. CIA becomes PA plus a vector of -1 to 1 times 1.96 times the square root of PA times 1 minus PA divided by NA. And CIB becomes PB plus a vector of -1 to 1 times 1.96 times the square root of PB times 1 minus PB divided by PB. And then so now we're going to make a bar plot. So our bar plot is bar centers becomes bar plot brackets, a vector of PA and PB, comma, names.arg equals a vector of control A, comma, treatment B, color equals a vector of steel blue and tomato, y limit, that's your limit of your y-axis, is a vector from 0 to max CIA2 and CIB2 times 1.2. Y lab, which is the label on your y-axis, is conversion rate. Main is the title of the bar plot, is A/B test conversion rates with 95% CI. And CI is your confidence interval. And then so we're going to add error bars. Arrows, brackets, XO equals bar centers. YO equals C, which is a vector of CIA1, CIB1. X1 is bar centers. Y1 is a vector of CIA2, CIB2. Angle equals 90. Code equals 3. Length equals 0.08. And line length equals 2. So we run the program, and this is the bar chart, the conversion rates bar chart that we've come up with, which is A/B test conversion rates with 95% CI, which is your confidence interval. So you can see the blue is control A, and the treatment in red is treatment B. So you can see here when we have written this program and we have simulated the data, you can see the control group is 12% and the treatment group is 18%. And that's what we've done in this simulation. And so with the control group, you've got your 12%, and with your treatment, you've got your 18%. So in this simulation, the treatment scores better than the control, but nevertheless, we still have a p-value of 0.269, which means there's no significant difference between the control group and the treatment group. So now that is the first A/B test that we've done, and it is using a prop test, a proportion test with a z-test, a two-proportion z-test. So now what we're going to do is we're going to cover another A/B test. We're going to use an Bayesian A/B test using the beta binomial model plus a posterior plot comparing the conversion rates of A versus B simulated. So now what we're going to do is we're going to simulate some data. And so what we're going to do when we simulate the data is we're going to set our seed so that every time you run the program, the variables are going to be initialized to the same values. So you type set.seed brackets 1, 2, 3, and you can type any value you want within the brackets. So in A is 200, in B is 200, and that's the number of samples. So the control converts at 12%, and the treatment converts at 18%. So conda A becomes R binom, that's a randomly sampled binomial distribution, brackets 1, comma, in A, which is 200, comma, 12%. And then conda B becomes R nom, that's a randomly sampled binomial distribution, brackets 1, comma, in B, which is 218%. And then so we're going to print conda A and conda B using the cat functions. The cat function is similar to a print function, but it allows you to print a text statement with the variable. So now what we're going to type is the posterior parameters of beta priors, comma, alpha 1 equals beta 1. But before we do that, let's just look at our conda A and conda B. So conda A is 21, conda B is 43, and probability of B greater is 99%. So now what we do is the posterior parameters of beta priors, alpha equals 1, beta equals 1. So we're going to calculate the posterior for A. So alpha A becomes 1 plus conda A. Beta A equals 1 plus brackets in A. That's 200 minus conda A. And now we're going to calculate the posterior for B. So alpha B becomes 1 plus conda B, and beta B becomes 1 plus brackets in B, that's 200 minus conda B. And now we're going to calculate the posterior probability that B is greater than A. So NSIM is 100,000. So post A becomes R beta, that's a randomly sampled beta distribution, brackets in sim, which is 100,000, comma, alpha A, comma, beta B. And then post B becomes R beta. That's a randomly sampled beta distribution, brackets M sim is 100,000, comma, alpha B, comma, beta B. And probably B greater becomes the mean of post A is greater than post B. And then so now we calculate posterior probability that B outperforms A. If the posterior probability is around 50%, the experiment is inconclusive. So we're going to type prob B greater than, and then that's going to give our prob B greater. So we're going to come down here again and look at our prob B greater. Your prob B greater is 99%. So since it's not 50%, it's not inconclusive. And so the probability that B is greater is 99%. So now we're going to plot the posterior distributions. We're going to calculate the density estimates. So we're going to put a density curve in the chart. So dense A becomes density brackets post A, and dense B becomes density brackets post B. And plot brackets dense A, comma, color equals steel blue, comma, line width equals 2, comma, main equals posterior distributions, conversion rates, and that's the title of the chart. X lab is the label of the x-axis equals conversion rate. Y lim is the limits of the y-axis is a vector of 0 to max density A $y, comma, density B $y. We're going to put some lines in there. Line bracket dense B, color equals tomato, and line width equals 2. We're going to put a legend in there. So legend brackets, top right. Legend is a vector that contains control A and treatment B. The color is a vector which contains steel blue and tomato. Line width equals 2 and BTY equals N. And so if the tomato curve B is shifted to the right, B is better. So that's just a note that I've got there. And so this is the chart that we have created, posterior distributions, conversion rates. And so you can see that the treatment is the tomato curve. B is shifted to the right, so that means the tomato curve is better. But we already know that the tomato curve is better because when we simulated the data, the control group was 12% and the treatment group was 18%. But when you're in a real world situation, you're not going to know what the control group and the treatment group are going to be. But this is just an exercise to show you how to perform A/B testing with Bayesian statistics, which I think is quite interesting indeed, because you got your control group A and you got your treatment group B, and the treatment group is shifted to the right, which means that the treatment group is better than the control group. But we already know that because we simulated our data to be that way. So now what we're going to do is we're going to do a bootstrap A/B test. And so a bootstrap A/B test is when you continuously take samples of your sample. And so this is just an example of how to conduct a bootstrap A/B test. The first thing that we're going to do is we're going to simulate our data. So you want to set your seed. The reason why you set your seed is so that every time you run the program, the variables are going to initialize to the same value. So you type set.seed brackets 1, 2, 3. You can put any number you want within the brackets. NA is 200, NB is 200. That's the number of samples. And so the control group is going to convert to 12%, and the treatment group is going to convert to 18%. So A is a randomly sampled binomial distribution of NA is 200, 1, 12%. And the treatment group is a randomly sampled binomial distribution of NB, which is 200, 1, 18%. And then we're going to observe our conversion rates. So PA becomes mean A, and PB becomes mean B. And the obs difference, that's observed difference, becomes PB minus PA. So we're going to print the observed difference. So we're going to use the cat function to print the observed difference. And the reason why is so we can print a text in there with the variables. So we're going to look at the observed difference and see what we come up with. Observed difference is 0.04, and your confidence interval is going to be negative 0.03 to 0.11. Now we're going to carry out our bootstrap sampling. In boot becomes 10,000. Boot diff becomes numeric of in boot. So that means it's going to be like a list or an array of 10,000 spaces in it. So this is going to be a blank array that's got like 10,000 spaces in it, because this array is going to contain 10,000 elements. And we're going to create a for loop. For brackets I in 1 to in boot. So A star becomes sample brackets A, comma, replace equals true. So what happens is you're going to sample the A, and every time you sample it, every time you take a sample, you're going to put that sample back into the array. So it's a replacement. It's sampling with replacement. So every time you take out a sample, every time you sample it and you take a number out, then you're going to put the number back in. And B star becomes sample brackets B and replace equals true. And boot diff I, and so because it is a for loop, this for loop is going to iterate 10,000 times, because in boot is 10,000. So boot diff I becomes mean of B star minus mean of A star. So you're going to have 10,000 means. Well, the difference between B and A, you're going to have the difference between B and A in this boot diff. So it's going to have 10,000 elements in it. And that's what you're going to be doing. So now we're going to have 95% bootstrap percentile CI. CI is your confidence interval. CI becomes quantile brackets boot diff, which is a vector of 0.025 to 0.975. So that means of the values in boot diff, it's going to be calculating the values of 2.5% to 97.5%. So if CI is above 0, B is likely better than A. If CI is below 0, A is likely better than B. If CI includes 0, the experiment is inconclusive. So what we're going to do is we're going to print the confidence interval, and CI is your confidence interval, and we're going to use the cat function to do that. So what that does is that allows you to print text in with your variable. So we're going to come over here and look at our confidence interval. So your confidence interval is negative 0.03 to 0.11. So what that's doing in this bootstrap example is that's telling you that it is inconclusive because the CI includes 0. So now we're going to plot the bootstrap distribution. Of difference in conversion rates. So we're going to create a histogram to do that. So you type hist brackets boot diff, comma, breaks equals 40, comma, frequency equals false, color equals light blue, main is your title, which is bootstrap distribution, difference in conversion rates, B minus A, X lab is your label of your x-axis, it's difference in conversion rates. Lines, brackets, density, brackets, boot diff, comma, color equals tomato, line width equals 2. So now we're going to add the conversion difference plus the CI, which is your confidence interval. So AB line, brackets, V, so V is telling you it's a vertical line, equals obs diff, color equals dark green, line width equals 2. And then AB line, brackets, V, telling you it's a vertical line, equals CI, that's your confidence interval, color equals black, line width equals 2, LTY equals 2. That's telling you that it's a dashed line. Now we're going to put a legend in there. So legend, brackets, top right, telling you that the legend is on the top right. Legend is a vector that contains density, observed depth, and 95% CI. Color is a vector that has tomato for density, dark green for observed depth, and black for 95% CI. Line width is 2 for all three. LTY is a vector, so for the density and observed depth, it's a straight line, and for the confidence interval, it's a dotted line, dashed line. And then BTY is in. So we run the program, and when we run the program, we have what looks like a normal distribution. And what this does is this falls in line with the central limit theorem, because the central limit theorem states that it doesn't matter what the distribution is. If you sample this distribution enough times, the means of the samples will eventually become a normal distribution. So this exercise also proves the central limit theorem, because the distribution that we had initially was a binomial distribution. So you had two binomial distributions for A and B, but you sampled it 10,000 times. And then because you sampled it 10,000 times, you came up with a normal distribution, which proves the central limit theorem. And then so you can see here in the legend that the red line is your density curve, the blue line is your observed difference, which is about 0.04, and the 95% confidence interval is the dashed black line. So when we did this test, since 0 is included in the confidence interval, that's telling you that the results are inconclusive, but I wanted to go ahead and do this for you anyway. So the next thing we're going to talk about is power analysis. And what power analysis does is it tells you how big your sample size needs to be. So what we're going to do is we're going to perform a sample of the power analysis so you can see how it works. So we're going to perform a power analysis for a two-proportion test. So P1 becomes 10% and it's blue and it's your control group. And P2 is 15% and it's red and your test group. Your alpha, which is also your significance level, is 0.05. The N per group becomes 500. So that's numbers per group. So we're going to compute the power. Power result becomes power.prop.test brackets N equals N per group, so that's the number of samples, comma, P1 equals P1, comma, P2 equals P2, comma, sig.level equals alpha, that's your significance level of 0.05, and the alternative equals two-sided. And then we're going to print our power result. So we come over here. So your power result is a two-sample comparison of proportions power calculation. N equals 500, P1 equals 10%, P2 equals 15%, significance level is 5%, power equals 0.667, alternative is two-sided. So that is our power result. So now the required sample size for 80% and 90% power. So for 80% power, N80 equals or becomes power.prop.test brackets power equals 80%, comma, P1 equals P1, P2 equals P2, sig level equals alpha, that's 0.05, alternative equals two-sided, and then you have a $sign in. And then for your 90% power, you have N90 becomes power.prop.test, brackets power equals 90%, P1 equals P1, P2 equals P2, sig.level equals alpha, alternative equals two-side, brackets $sign in. So now we print N80 and N90, and that's the number of samples for 80% and 90%. So we come over here, we look at the number of samples. For 80%, you have 685 or 686 samples, and for 90 samples, you have 917 or 918. So that's how many samples you need for the percentage that you want. So now we're going to calculate a power curve for sample sizes 100 to 2,000 per group. Sample sizes becomes, and it's another vector, it's a sequential vector of 100, 2,000 by 50. And then power values becomes S apply, bracket sample sizes, function N, and then N is going to be your sample, it's going to be the number of samples. And then the function is power.prop.test, brackets N equals N, which I think it is, let's see what it says. Doesn't tell you what N is, but N per group is 500. So, and then you have N80 and N90. And then P1 equals P1, P2 equals P2, sig.level equals alpha, that's 0.05. Alternative equals two-sided, and that's brackets $sign power. So now what we're going to do is we're going to plot brackets sample sizes, power values, type equals L, letting you know it's a line, and line width equals 2, and the color equals tomato, The main, which is your title, is power curve for A-B test. Differences equals 5%. X lab is the label on your x-axis, is sample size per group. Y lab, which is the label on your y-axis, is power. Y limit is a vector from 0 to 1. And then we're going to put some horizontal lines in there. AB line equal brackets H, letting you know that it's a horizontal line, equals 80% or 0.8, comma, color equals steel blue, LTY equals 2, letting you know that it's dashed. AB line brackets H is horizontal, equals 0.9, comma, color equals steel blue, LTY equals 2, letting you know that it's dashed. And we're going to put some text in there. So text brackets 1500, comma, 0.82, comma, 80% power, comma, color equals steel blue, and then text brackets 1500, comma, 0.92, comma, 90% power, comma, color equals steel blue. And then so we run the program, and this is the chart that we come up with. It's a power curve for A-B test. Difference equals 5%. So you see that you've got the 80 percentile line, which is at 80%, and you've got the 90 percentile line, which is 90%. So the 80 percentile line is just over 500, and the 90 percentile line is close to 1,000. So you can determine any number of samples that you want using this algorithm, which is going to tell you the optimum number of samples for your test. So the next thing we're going to do is we're going to actually carry out an A-B test. And then what I decided to do was I decided to use 1,000 samples. So that's pretty close. It's over 80% and it's over 90%. So we're going to have an example of an A-B test to see if a red website, which is the test site, gets more clicks than the blue website, which is the control site. So your null hypothesis is there is no significant difference between the control and test websites. And the alternate hypothesis is there is a significant difference between the control and test website. So we're going to simulate the A-B test data to do this. So blue is your control group and red is your test group. So the first thing we want to do is we want to set our seed. The reason why we set our seed is so every time we run the program, the variables are going to set up, initialize to the same values. So you type set.seed brackets 1, 2, 3. You can put any number that you want within the brackets. So in blue, that's the number of samples for the blue test. Blue set, which is your control set, is 1,000. And in red, that's the number of samples for the red set, which is your test set. So blue is going to convert at 10%, and red is going to convert at 15%. So you already know, because we're simulating this data, so you already know that red is going to perform better than blue. But this is simulated data. And so the thing is whenever you're doing this test in real life, you're not going to be simulating data. You're going to be using real data. So you're not going to know which group is, whether the test is going to outperform the control or not. So blue clicks becomes R binom. That's a randomly sampled binomial distribution. Brackets in blue, that's 1,000, 1, 10%. So that uses a binomial distribution because the person clicks or does not click on the site. And then red clicks becomes R binom, which is a randomly sampled binomial distribution. Brackets in red, which is 1,000, 1, 15%. And so the binomial distribution reveals either a yes or no answer. So we're going to calculate the conversion counts. So conv blue becomes sum, brackets, blue clicks, and conv red becomes sum, brackets, red clicks. Because you know the answer that you're going to get on this binomial or binom is either going to be a 1 or a 0. So a sum is going to be how many blue clicks you've got or how many red clicks you've got. And then we're going to calculate the conversion rates. So P blue becomes conv blue divided by N blue. So N blue is 1,000. So what you're doing is you're calculating the number of clicks and you're dividing it by 1,000. And that's the same with red. So P red becomes conv red divided by N red. So you're going to calculate the number of red clicks divided by 1,000. And then now we're going to print off the obs diff. So let's see what the obs diff is. Your obs diff is 0.47. So that's 4.7% is your obs diff. And if you want to print this, you can type this. You can type cat that's the difference of the observations. And this is next line. So I'm going to run it again. And I'm going to hope for the best. It's just taking a little while. Okay, so you can say here, it says obs diff 0.47, which is 4.7%. So now we're going to perform a two-proportion z-test, which is prop.test. Test result becomes prop.test brackets. X is a vector with conv blue and conv red. N is a vector with N blue, N red. Correct equals false. And then we're going to type test result. So we're going to see what the test result is. So this is a two-sample test for equality of proportions without continuity correction. Data is a vector containing conv blue, and conv red out of a vector of N blue and N red. And x squared equals 10.811. Degree of freedom equals 1. So you calculate your degree of freedom by taking the number of samples, which is 2, and subtract 1 from those number of samples. So 2 minus 1 is 1. P-value is 0.001. So since the p-value is less than the significant level of alpha, then what's going to happen is you're going to reject the null hypothesis in favor of the alternate hypothesis. So the null hypothesis is there is no significant difference between the two samples, and the alternate hypothesis is there is a significant difference between the samples. So because we're going for the alternate hypothesis, we're saying that there is a significant difference between the two samples. So the 95% confidence interval is 0.07 to negative 0.07 to negative 0.19. The sample estimates for Prop 1 is 0.92, which is 9.2%, and Prop 2 is 0.139, which is 13.9%. So now we're going to plot our conversion rates. So for 95% CI, or confidence interval. So 95% CI for each group. CI blue becomes P blue plus a vector from -1 to 1 times 1.96 times square root of brackets P blue times brackets 1 minus P blue divided by N blue brackets. And CI red, that's your confidence interval for the red, becomes P red plus a vector of -1 to 1 times 1.96 times square root of brackets P red times brackets 1 minus P red brackets divided by N red. And then we're going to create a bar plot with all this information. So centers becomes bar plot brackets C, that's a vector of P blue and P red, comma, names.arg equals a vector, which is blue control, comma, red test. Color is a vector with steel blue for the control and tomato for the test. Y-lim is the limits on the y-axis, which is a vector from 0 to maximum CI blue 2, comma, CI red 2 times 1.2. Y-lab is your label on your x-axis, which is your click-through rate, and main is your title, being A/B test, colon, CTR comparison with 95% CI. We're going to put some error bars in there, and arrows, brackets, XO equals center, YO equals a vector of CI blue 1, comma, CI red 1, X1 equals centers, Y1 is a vector of CI blue 2, comma, CI red 2, angle equals 90, code equals 3, length equals 0.08, and line width equals 2. And then so we're going to run the program, and this is what we come up with. This is the A/B test CTR, that's click-through rate comparison with 95% confidence interval. So you can see your blue group is your control group, and we had that set up for 10%. So you can see the blue group is less. And then your red group is your test group. And I think we had that set up for 12%. I think, 15%. Wasn't 12%. So since this is data that we have simulated, so with the blue group, it is 10%, and with the red group, or the tomato group, it is 15%. So basically, we had a p-value that was below the significance level of 0.05 or 5%. So that meant you have to go with you reject the null hypothesis in favor of the alternative hypothesis, and you say that there is a significance difference between the control group and the test group. So that's basically how this works. But let's just see what happens. We're going to just change this just a tiny little bit. We'll say the red is 11%. We'll run that and say the red is 11%. So the p-value is 1. So the p-value is 100%. So since the p-value is 100%, you're going to fail to reject the null hypothesis. The 95% confidence interval is negative 0.02 to positive 0.02. And then we look at the chart we have created, and you can see that there is no significant difference between the control group and the test group. But what I'm going to do is I'm going to take this data and I'm going to put it back to where it originally was. But before I run it, I just want to say that the proposal for 1 was 9.2%, and the prop 2 was 9.2% as well. So that was almost equal, even though the blue group had a 10% click-through rate and the red group had a 11% click-through rate. The values came out to be the same. So we'll run it again, just so you can see for yourself. And what you can do is you can experiment with A/B testing yourself. You can experiment with A/B testing yourself. But what I wanted to do was I wanted to give you an A/B test from start to finish, and then I also wanted to show you how to determine the correct sample size. But in reality, the larger the sample, the better the result you're going to get. And that's what that power graph showed. It showed that the more numbers of samples you have, the higher percentage of accuracy you're going to get. So you want to have the sample as high as possible. And so that's why I chose a sample size of 1,000. But that concludes this video, and it concludes the video on hypothesis testing. I've included all of the hypothesis tests for different scenarios that you can experiment with. So the next video I'm going to make is on experimental testing, but I do hope that you got something out of this video and that you're going to watch the next video as well. So I will be communicating with you in the next video.